Everyone knows the name of the first of the planets in our solar system. Mercury was first seen in ancient times and carries the name of a Roman god. We've known of its existence for thousands of years. It is not hidden in darkness, but thanks to its position next to the Sun, it is bathed in brilliant light. And yet, it is the least explored terrestrial planet, having only been visited by 2 probes in all of our spacefaring history. Why is that? Is it boring? What do we truly know about Mercury? What are its characteristics and history, and how have we learned about it? I'm Alex McColgan, and you're watching Astrum. And in watching this supercut, you're about to find out. Join with me as I teach you everything you might want to know about the first planet in our solar system, Mercury. Now, when you think about the physical characteristics of Mercury, I'm sure you imagine it being the closest planet to the Sun, but also that it's this giant rock floating in space. You wouldn't be too far wrong with that, but it is much more interesting than what you may first think. For example, when I look at Mercury, I do think of our moon. But Mercury actually is visually more appealing than our moon. Look at it in its true color. The first thing that I notice is that it actually does have a color. It's not just different shades of gray. And what else? Well, did you know, for example, that Mercury consists of approximately 70% metallic and 30% silicate materials? It's actually more metallic than rocky. Because of this, Mercury's density is the second highest in the solar system at 5.427 grams per centimeter cubed, only slightly less than the planet with the greatest density, that of Earth, at 5.515 grams per centimeter cubed. If Mercury happened to be the same size as Earth, that would mean it would have pretty much the same gravitational pull as its surface. But being the size that it is, its surface gravity is only 3.7 meters per second squared. If you were to compare its gravity to Earth, it would look something like this. This means the surface gravity of Mercury is only slightly less than what it is on Mars, and considering that Mars is a much bigger planet, that just says something about the density of Mercury. Before we leave the subject of Mercury's size, I want to show you one last comparison, that of Ganymede and Titan against Mercury. Now, Ganymede is the solar system's biggest moon and also the biggest moon of Jupiter, while Titan is Saturn's biggest moon and the second biggest moon in the solar system. These 2 giant moons are bigger than Mercury, as you can see here, but their masses are far less. If you look closely at Mercury's surface, you'll see its appearance is similar to that of our moon. It shows extensive mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. But it obviously was geologically active at one point, because one of the distinctive features of Mercury's surface is the presence of many narrow ridges extending out to several hundred kilometers in length. We'll talk more about these later. One of the most distinctive things you'll notice about Mercury is this huge crater on its surface, called Caloris Basin, with a diameter of 1,550 kilometers. The impact that created Caloris Basin was so powerful it caused lava eruptions and left a concentric ring over 2 kilometers tall surrounding the impact crater. At the antipode of Caloris Basin is a large region of unusual hilly terrain known as the Weird Terrain. If you compare this region to the rest of Mercury, you can see why it would have this name. So, what's it like on the surface of Mercury? Well, to start with, the surface temperature is hugely different all over. It can range from minus 173 degrees Celsius to over 400 degrees Celsius. It never rises above -93 degrees on the poles, though, because there's no atmosphere retaining the heat. This means that there's quite a big difference between the equator and the poles, but this variation is also due to its orbit and rotation, which we'll get back to later. The subsolar point reaches about 400 degrees, while on the dark side of the planet, the temperatures are, on average, -163 degrees Celsius, because Mercury is too small and hot for its gravity to retain any significant atmosphere over long periods of time. It's not able to retain any of the heat it gets from being so close to the Sun, which is why the dark side of the planet is so much colder than the side facing the Sun. Mercury, however, does have an exosphere, which is like an extremely thin atmospheric-like volume surrounding the planet. Molecules in an exosphere are gravitationally bound to a planet, but the density is so low that it can't behave like a gas because the molecules don't collide with each other. In this picture, you can see the MESSENGER probe's view of Mercury's exosphere. When solar wind hits the planet, it rips off certain atoms out of the exosphere, and what's left is this trail of atoms going into space. We call this the planet's tail, and every planet has this to a certain extent. Earth even has an exosphere, but it starts at 600 kilometers above the surface. It's really the point where space and the atmosphere meet. Now, in the case of Mercury, this exosphere is not at all stable. Atoms are continuously lost and replenished from a variety of sources, which we'll discuss in more detail later. NASA has been able to confirm that craters at the North Pole of Mercury contain water ice. Mercury also has something which Mars lacks: an actual magnetosphere, or a magnetic field all around the planet. It is only about 1.1% as strong as Earth's, but it's still strong enough to deflect a lot of the solar wind around the planet. Now, we're going to get to one of the things which I find the most interesting about Mercury: its orbit and its rotation. Mercury has the most eccentric orbit of all the planets, with its distance from the Sun ranging from 46 million kilometers to 70 million kilometers. Now, this is something a bit hard to imagine, but bear with me. Mercury takes about 88 Earth days to complete an orbit around the Sun. It also has a 3-to-2 spin-orbit resonance of the planet's rotation around its axis. This means it spins 3 times around its axis for every 2 times that it orbits around the Sun. It takes about 59 Earth days for Mercury to rotate on its axis once, which is what we call a sidereal day. By pure coincidence, this is almost exactly half its synodic period in respect to Earth, which is 116 days. So between conjunctions of Earth and Mercury, Mercury rotates on its axis exactly twice. Historically, there was a big problem with that. Because of this coincidence, we believe that Mercury was tidally locked to the Sun for the longest time. You see, Mercury orbits closely around the Sun, meaning it was always tricky for astronomers to get a good look at it for most of its year. When it finally got in a good viewing angle from our perspective, we'd have a look at the face of the planet. 118 days later, we'd have another look during this prime observation alignment and see the same face again. So to them, it showed that Mercury was tidally locked to the Sun. What astronomers didn't realize is that Mercury had rotated exactly twice on its axis during this time. It wasn't until radar observations of the planet that we found out it does rotate slightly faster than it orbits. This 3-to-2 orbital resonance means that if you were actually standing on Mercury, it would appear that one day, from sunrise to sunrise, or what is called a solar day, is 2 Mercurian years. Standing on Mercury, that would look something like this. You would see the sun rise relatively fast, and then, as it approaches midday, it slows down and even starts going backward before continuing on again to sunset. As you can see, that took a whole year, which means nighttime on Mercury also takes a year. The sun starts going backward in the sky because approximately 4 Earth days before perihelion, the speed at which Mercury travels along its orbit equals the speed at which it is rotating. At this point, the sun's apparent motion stays stationary. At perihelion itself, Mercury's orbital speed exceeds its rotational speed, so to a person actually standing on Mercury, the sun appears to move backward. 4 days after perihelion, the sun's normal motion resumes. You can see this even clearer from a top-down perspective of Mercury. Twice a day, on one of its poles, the sun seems to pause and then continue on again. Something else to note about Mercury's orbit is that it's inclined by 7 degrees to the plane of Earth's orbit. As a result of this, we can only see Mercury transit in front of the sun when it's directly between us on Earth and the sun itself. And because its orbit is inclined by 7 degrees, this only happens about once every 7 Earth years. The last thing we'll discuss about the rotation of Mercury is that its axial tilt is almost zero, with the best measured value as low as 0.027 degrees. This is even smaller than that of Jupiter, which has been measured at 3.1 degrees. And finally, do you want to see Earth from Mercury? Well, here we are, just a couple of pixels across. This photo was taken from the Messenger probe several years ago, and barring newborns, every single one of us was in this picture. But what was Messenger, and why was it important? Well, let's start with a little context. When mankind first started sending spacecraft out to explore the solar system, the first planet to be visited was Venus, our closest neighbor, in 1962. Next was Mars in 1965, and then Jupiter in 1973. Only then came Mercury in 1974. And already, this order might seem a little odd. The closest distance between the Earth and Mercury is 77 million kilometers. In fact, it is the closest planet to us on average. The closest distance between the Earth and Jupiter is 588 million kilometers, almost 8 times that. And Jupiter was visited again in 1974, twice in 1979, in 1992, in 1995, in 2000, in 2007. Multiple missions were launched to Saturn, Uranus, Neptune, to comets and asteroids, while Mercury got nothing for 30 years. Is this because it was deemed uninteresting? Did we discover everything there was to discover about it with that single first mission? Remember, that first mission was a flyby and only mapped about 40 to 45% of Mercury's surface. Actually, the real reason is that Mercury is one of the most challenging planets to visit in our entire solar system. Why? Well, as previously mentioned, Mercury exists in a furnace. Due to its proximity to the Sun, its surface temperature reaches highs of 430 degrees Celsius, so any probe visiting it would need to be highly heat-resistant. But that same proximity to the Sun means that any probe launched toward it will accelerate faster and faster due to the immense gravitational pull from our star. Using rocket fuel against, that would be like swimming up whitewater rapids. Combating the Sun's gravity required too much fuel for a Discovery-class spacecraft to carry, and slowing down the spacecraft enough to be caught up in Mercury's orbit seemed impossible. It was a question of weight. Weight is a challenging limitation when it comes to spacecraft. The heavier a craft, the larger a rocket needed to get it out of Earth's orbit, and the more expensive everything becomes. Scientists try to keep everything as light as possible to reduce this cost. As fuel takes up precious weight allocations that could go towards scientific instruments, scientists try to take only what is necessary to help them complete their journey. However, for about 30 years, scientists could think of no way to put enough fuel on a probe to get it to slow down enough to enter Mercury's orbit, especially if they wanted scientific equipment on board too. So after the success of Mariner 10's flyby missions of Mercury in 1974 to 1975, Mercury exploration was put on hold. But in 1985, an orbital mechanics expert named Chen Wanyan realized that there was a way of getting a probe into orbit around Mercury that didn't need new technology. Instead, she had worked out a particular route an orbiter could take around the solar system that would slow it down enough to enter Mercury's orbit with only a few course corrections. Rather than going straight to Mercury, the orbiter would need to take a longer way. How long? Under Chen Wanyan's model, a craft would orbit the Sun about 15 times, flying past Earth once, Venus twice, and Mercury 3 times, before finally slowing down enough to enter its orbit on the 4th pass. All these planetary flybys would be essential. By skimming the planet's atmospheres, vital speed could be shaved off from atmospheric drag and due to the gravity of the planets. The entire route would cover a mammoth 7.9 billion kilometers and would take 6.5 years. Chen Wanyan's findings were not immediately picked up, but in 1998, NASA began to take an interest in the idea, and after seeing the feasibility of the route, they launched the Messenger probe in 2004. Messenger, or the Mercury Surface, Space Environment, Geochemistry, and Ranging probe, was only 1.8 meters long and 1.3 meters wide and weighed 1,100 kilograms. This is small and light for a typical NASA mission. Just for comparison, Juno is 20 meters long. Messenger came equipped with a powerful thruster, a ceramic heat shield to protect it from the sun, 2 solar panels, and a whole suite of scientific equipment for imaging and measuring data from Mercury. Scientists hoped to take advantage of this opportunity to learn as much as they could about the chemical composition of Mercury's surface, its geological history, its magnetic field, and its core, among other things. Messenger spent its first year in space making one orbit around the Sun before meeting back up again with Earth. This gave scientists a chance to test its equipment on a known astronomical body, to make sure there weren't any errors, and to make any adjustments as needed. Messenger took some photos of Earth and the Moon, and also tested its other equipment to take readings of our atmosphere and magnetosphere. Fortunately, everything was working perfectly. As it began to head further sunward, Messenger employed a clever technique to help reduce its acceleration toward the Sun. It used its solar panels to catch solar radiation, like sails on a ship might catch wind. Solar radiation, hitting an object, actually pushes it very slightly. While this force is very tiny, because Messenger's journey was so long, it really added up. Making the most of this phenomenon was one of the ways Messenger saved propellant and decelerated naturally. The next notable landmark in Messenger's journey came in 2006 when it did its first flyby of Venus. Sadly for scientists, this moment came at a time when Venus was exactly on the opposite side of the Sun from Earth, which meant Messenger was not in radio contact. It did take some photos of the planet, which it later sent, but otherwise performed no science. However, in 2007, it passed Venus again. At that time, another spacecraft was orbiting Venus, ESA's Venus Express. Messenger and the Venus Express took the opportunity to work together, performing the first-ever simultaneous measurements of particle and field characteristics of the planet. But then it was on to the main event, Mercury. Messenger made its first flyby of Mercury on January 14, 2008, with everything going smoothly. The same was true of the second flyby. But during the third flyby, in 2009, something went wrong. Messenger went into safe mode, which was designed to protect systems on the craft in the event of an error. How disappointing to have come so far, only for the mission to potentially fail during one of the final stages. Messenger remained in safe mode for what must have been 7 hours of stress for all of the scientists involved. You see, Messenger had to pass through Mercury's shadow during this flyby, meaning it had to rely on its batteries for 18 minutes. Something wasn't configured right in the power management part of the software. Fortunately, Messenger's computer reset once power from the panels, charged the battery, and it was able to continue with its mission, swinging around the Sun one more time before finally entering orbit around Mercury on March 11th, 2011. Messenger took up an elliptical orbit around Mercury, alternating between as close as 200 kilometers and as far away as 15,000 kilometers. This is because Mercury acts sort of like a giant sun mirror, radiating heat back into space. Remaining too close to Mercury was too hot for Messenger, even with its heat shield, which was more designed to protect it from the Sun, 7 times brighter by Mercury than it is on Earth. So moving further away, every 12 hours, gave it a chance to cool off. Messenger spent the next 4 years in Mercury's orbit, far exceeding scientists' hopes and expectations for the mission, as they had originally planned for it to last only 1 year. Before launch, scientists had hoped that Messenger would take at least 1,000 photos over the course of its lifetime. However, Messenger took over 200,000 photographs, giving us a complete map of Mercury's surface in high resolution and color, as well as photographing nearby comets and other planets. On December 25th, 2014, Messenger's propellant, so carefully saved up until that point, was finally about to run out. By this point, Messenger was orbiting a mere 25 kilometers from the surface of the planet. Scientists gave the thrusters one last burst to extend its orbit for as long as possible, but on April 30th, 2015, Messenger crashed into the surface of Mercury. After a journey that had lasted over a decade and had covered literally billions of kilometers, Messenger's journey had come to an end. Messenger gave us a wealth of insights into Mercury before it died. On board Messenger were a host of scientific instruments, including a magnetometer to map out Mercury's magnetic field, which is thought to be generated by a dynamo effect in its molten core. Our fast rotation and tidal stretching from our moon keep our core molten, but Mercury doesn't have a moon or a fast rotation. What it does have, however, is an eccentric orbit, more so than any other planet. Gravitational strength increases and decreases as it gets closer and further away from the Sun, so the tidal forces pull and squeeze on the planet, the friction of which keeps Mercury's core hot and the dynamo going. Unlike Earth's, it is offset from the center by about 20% of the planet's radius, and we don't really know why. Its magnetic field is only about 1% as strong as Earth's, but this still has an impact on deflecting a lot of the solar wind around the planet. However, due to it being closer to the Sun, the solar wind pressure is a lot greater here than it is around Earth. Add a weak magnetic field to the mix, and the magnetosphere around Mercury is compressed closely to the planet's surface. Earth's, on the other hand, extends many times the diameter of the planet away from the surface. Interestingly, these factors make the magnetosphere of Mercury highly dynamic. What does this entail? Well, for one, reconnection events are 100 times more common around Mercury than around Earth. Reconnection events occur when magnetic field lines snap together as the charged solar wind pushes against a planet's magnetosphere. When this happens, it allows a few of these charged particles to break into the planet's magnetosphere, entering a region of plasma in the planet's magnetotail. The flows you see in this simulation in the plasma region are from reconnection events. Another feature of the magnetosphere that MESSENGER detected was energetic bursts of electrons, producing hundreds of thousands of electron volts of energy. As MESSENGER orbited Mercury, it picked up thousands of these events, and mysteriously, they were mainly localized in the northern hemisphere and were compressed toward the planet, along the sun-facing side. This is still an ongoing field of study. However, scientists believe these electrons have been accelerated through breakdowns in the magnetotail, and they follow the direction of the magnetic field around from the South Pole to the north. MESSENGER also hosted a wide array of spectrometers. Spectrometers are important for detecting the composition of mineral deposits on the surface without having to actually take a sample. Spectrometers can also be used to detect the particles in the atmosphere. Now, Mercury doesn't have an atmosphere per se, but as previously mentioned, it has an exosphere, or an extremely tenuous atmosphere. It is so thin that the particles within it don't interact with each other. But what MESSENGER found out about this exosphere's relationship to the surface really surprised scientists. Mercury is covered with volatile substances. It isn't just a fried, rocky planet. It seems to be covered in potassium, magnesium, sulfur, sodium, and chlorine at a higher level than any other terrestrial planet, and much higher than on our moon. The fact that its volatile ratios have more in common with Mars than with Earth and Venus has completely disproved a lot of solar system formation theories that existed before MESSENGER arrived at Mercury. These volatiles are blasted by radiation from the Sun, more so at the equator than near the poles, which may explain why, on the surface, some substances, like potassium, are more abundant in the northern hemisphere than around the equator. It is much hotter on Mercury around its equator than at the poles, so the potassium there would have been heated enough that much of it has been lost from the surface to the exosphere. Now, the exosphere contains a lot of the particles you would also find on the surface, like sodium, potassium, and the others I mentioned. This exosphere is not at all stable. Solar wind picks up and carries away a lot of charged particles, and solar light pressure also pushes a lot of the neutral particles away. Were it not for the processes that replenish the exosphere, Mercury would lose it all to space over a relatively short time frame. While most substances certainly do come from the planet's surface, it also contains other elements like hydrogen and helium, which cannot be found there. So where did they come from? Well, as you may know, the Sun is made predominantly of hydrogen and helium, and interestingly, the solar wind carries these particles to Mercury. Some of the solar wind actually gets caught up in the exosphere and stays for a while. As far as we know, this is the only major source of hydrogen and helium in the exosphere. The particles that do get stripped away have been spotted by Messenger 2. In these images, we see calcium, an unknown process of which means it's much more prevalent in the exosphere during the planet's dawn than dusk, and magnesium streaming away from the night side of the planet. In fact, Mercury's tail has been known about for a while. In these images, sodium ions are lit up as they stream away from the planet, making Mercury look like a comet. Incredibly, if you were to look up into the night sky on Mercury, you would actually see a faint yellow glow, reminiscent of city lights on Earth. This tail is seasonal. The eccentric orbit of Mercury means that its distance to the Sun varies throughout its year, and as it orbits, its orbital speed also changes. So the time of greatest sodium emission is actually when Mercury is at its middle distance from the Sun. There was one other curious substance found in Mercury's exosphere that scientists really weren't expecting: water vapor. This could come from cometary tails as they pass by, or it could come from ice deposits, Messenger, detected around the planet's poles. Surprisingly, water ice can exist on this scorched planet, but only at the bottom of permanently shadowed craters, forever protected from directly interacting with the Sun's light rays. The Earth-based Arecibo radio telescope had already detected highly reflective regions around the poles, and as images from Messenger came in, these regions matched up with regions of permanent shadow at the bottom of large craters. Estimates put the amount of water ice found on Mercury at a quadrillion kilograms. This isn't huge by Earth standards, but it would be a significant boost to any